Hey everyone, welcome to another QGSS Q&A. Today we have the amazing Joana Fraxanet, who talked to you guys through some algorithms, and we're so excited to have you today, Joanna. Please feel free to put questions in the chat or in the Q&A. I know there were some leftover questions from the lectures that weren't answered, so again, please put them in the chat or the Q&A, and we'll get to them. Any starting words, Joanna?
Well, hello everyone. It's nice to be here. And I saw also that during the talks there were some questions, so feel free to put them here and we'll answer them now.
Awesome. So let's go ahead and dive into it. The first question is, how can QML benefit physics research?
So I think in many ways, one thing that is important with QML that maybe I was mentioning in the lecture is that I think many QML algorithms like quantum classifiers and this kind of algorithms make sense for like they tend to work better for quantum data. So data that you already have in your quantum circuit, so you kind of don't need to do this type of mapping. And this could also be the reason to have an advantage, the fact that the data is already expressed in the quantum circuit and then probably doing it classically would make a lot of overhead. So then using classifiers on, for example, ground states that you have obtained from a VQE so that the whole algorithm is already within the quantum circuit or this kind of stuff could be interesting. In fact, I know, for example, people were using this kind of classifiers to map different phase diagrams of materials, for example, or different types of spin models or things like this. Um, but yeah, but they can be used for this type of research. Also quantum kernels. There's different types of algorithms that I also didn't mention in the lecture because I was saying that the QML part I kept it a bit shorter, but there's definitely a lot of options.
That's so exciting. And then our next question is, what does it, ooh, I just lost the question. Give me one second. What does it mean to make the error poly errors? It was a random error, then it becomes a bit or a phase. How does that work?
So Pauli errors really means that you can express the error as the action of a Pauli matrix. So then basically, when you apply random Pauli matrices in your state, like throughout the circuit, for example, when you perform a gate, if you have the action of a Pauli matrix before, this could be expressed within the error model that it's like Pauli noise or a Pauli noise channel. Then you have a bunch of like research and more rigorous explanations of what really this means and what are the consequences of this kind of noise. But that's the easy answer, let's say.
Yeah, I think you put that really eloquently. And then our next question is, what is the real interest in the bipartition after minimizing the cost function for the Hamiltonian?
Ah, yeah, this one I saw it during the lecture, and I was actually looking for different examples in which like the max cut problem can be used for use cases. I guess this is more or less the question. And for example, solving the max cut apparently it's interesting for I don't know some kind of network problems, or if you can express some kind of they were saying, for example, for quality of a product, and then you have different products, you relate them, and you want to find the bipartition that kind of separates the ones that have the most differences, or this kind of optimization problems that in industry could be very interesting to solve more efficiently. In general, yeah, whenever you can, there's many optimization problems, like abstract optimization problems that then apply to real world problems that you can map in the form of some Ising Hamiltonian and then try to solve, for example, with QAOA, as we were doing for this max cut problem.
Very cool. And then the next question is one that I've heard a couple of times, which is SQD better than VQE for quantum chemistry applications? How would you classify both of those solutions?
Yeah, so I guess you've been hearing a lot of SQD, and probably this is next week, but there's going to be some talk specifically on the details of that. And it's quite exciting. It's a different way of treating these problems. The main difference is with the measurement bottleneck that I was mentioning. So with quantum chemistry, the problem we have is that the Hamiltonian has a lot of Pauli strings. So if you want to measure these expectation values, you need to do a lot of executions of the circuit and obtain a lot of measurements. And this makes some instances of VQE for large molecules very difficult to run on hardware. SQD solves this problem. Then, of course, SQD has its own problems, and as I said, you're going to hear more about them, but it's still a matter of like figuring out whether in some cases it can show an advantage and over like some other kind of classical algorithms. And it compares to VQE, but yeah, like the main difference would be that we're able to bypass this kind of measurement problem. And also that I think it's interesting, this kind of algorithms that, so SQD is taking part of the generalization in the classical part of the algorithm in HPC. And this kind of mix of quantum and HPC is pretty interesting, and it's something to explore. So I think we're going to see there's this first paper of SQD, and now there's already several variations that have been published, and we're going to see more and more improvements, and some of them are going to be inspired by the training loops, for example, of VQE.
That's really exciting. And then our next question is, can you explain the concept of fractional gates? How do these manifest themselves in the circuit and how do they reduce circuit depth?
So fractional gates, if you search in the documentation of Qiskit, some of them now can be that can be implemented. In particular, this works for the RZZ gate and the RX gate, and it's ways of implementing them in the hardware that by doing shorter pulses. So in a way, like to implement the RZZ gate, you have to do some rotation Z gates, some ZZ gates, and some rotations and so on. And there's ways of kind of compressing these into a shorter gate. And that's why they're very interesting in cases in which you have these types of gates. They reduce the depth of the circuit. On the other hand, there's things that, for example, right now cannot be implemented with fractional gates, like the Pauli twirling technique that I was mentioning right now. It's not available for this kind of gates just because they work a bit differently.
And I see a follow-up question that is asking, um, in terms of fractional gates, how advanced do you need to be to use them?
I mean, to use them with Qiskit, you just need to enable the fractional gates and then it does it for you. So yeah, not that much. In fact, it's very easy to try if you have this kind of gate that allow for the fractional gate implementation. Then yeah, the only thing to take into account is that some of the error mitigation then might not work for that. But yeah.
Yeah, it's super easy to try stuff out at least, which is good.
Yeah,
And
exactly.
then our next question is how to parallelize Qiskit codes for complex calculations.
I'm not sure I understand what do you mean by parallelize?
Yeah, Prince, if you could reframe your question and then we'll get back to it if that's all right, because I also am a little confused by what you mean by paralyze.
I mean, just because whenever we send a job to the hardware, this is taking the whole hardware. So you're using the whole
Right.
QPU to run that execution, that circuit. So in principle, this is not parallelizable, but maybe you meant some other part of the code.
Yep. We'll wait to hear back from you, Prince.
Yep.
Does the nonlinear channel make the error correction more difficult?
Uh, Also, I would ask what you mean exactly here by error correction. I was in the talk, I was mentioning error mitigation and error suppression techniques. Then if we talk about error correction, I guess there's going to be other sessions about this, but then we're thinking about a full implementation of error correction. That error correction in principle is able to correct for any type of noise. For error mitigation and error suppression, as you see, how each technique is able to correct, like to cancel or mitigate certain types of noise. So whenever you have Pauli noise, this is better because it accumulates more linearly and this kind of details, but it depends on the technique.
Got it. And then I've seen this question a couple of times. Um, what are some problems, research projects, challenges that I can apply, um, sort of what we were learning in quantum algorithms to?
I think so I guess that you mean the talk with variational quantum algorithms. In general, you can try one of the algorithms that I mentioned using VQE. If you want to do it for quantum chemistry for small molecules, I think it's nice, and then you learn a lot about how to build these Hamiltonians for a molecule and so on. And there's ways of like there's a lot of tutorials in the learning platform on how to do this. You can also try one of the optimization algorithms like QAOA. And then now with the add-ons, you also have access actually to the code to implement SQD, even though as I said before, you're gonna hear more about it soon. But yeah, in general, doing some kind of optimization problem or quantum chemistry problem with VQE that could be examples to apply this kind of variational algorithms, or QML also. But yeah, I think the like first implementing it for small systems is kind of easy, or like it would be the first step. Like scaling this up to larger systems, which is where things start to become more interesting, and you need to take into account everything that was mentioned also in the practical quantum techniques, so all the error mitigation and all this kind of stuff.
Yeah, I really love your call out to the learning platform because I think that's a
Yeah,
great resource and what I used to do my research when I was an undergrad. And then also I love the teasing to the SQD lectures that are coming up. Um,
definitely.
so
And sorry,
go ahead.
sorry. So and you have the lectures there, but you also have several tutorials in which you have the really the Qiskit code, and you can kind of copy this and adapt it to a bit of a different problem. I think this is a very good starting point.
Got it. And then our next question is how does backpropagation work in quantum machine learning?
Yeah, so this was the part where I was discussing this problem of getting the gradients out of the quantum circuit, and this means having to do more executions of the quantum circuit in order to compute the gradients that then later are going to allow you to do the backpropagation, no? Because once you have the direction in which you have to move your parameters through the gradient, then you basically change these parameters a bit and you execute the circuit again. And there's different ways. There's the parameter shift rule that is used to obtain gradients, in which you make use of the fact that the rotations, that is the way in which we encode the parameters in the quantum circuit, they're kind of they are expressed in terms of cosines and sines, and then you can rephrase a bit the derivatives, and but you still have to do more circuit executions, or then you can compute the gradients also using some approximate expressions for derivatives. And once you have that, you just implement backpropagation in the same way as you do for classical machine learning. And then instead of backpropagation, you also have other optimization algorithms that you can use. In fact, in Qiskit, you can see the whole list, and you can choose which kind of optimization you want to use. And here there's also a lot of details, and it becomes a complicated topic because optimization field, like classical optimization, is very old, and there's a lot of things that are done. That's also why also it's difficult to compete against classical algorithms. Like this is a very advanced field. Hmm.
No, I really like that point that oftentimes we're building off of classical and then they're like one-upping us in a way. But that is a part of the process as we sort of fine-tune this technology.
Exactly. Yeah, yeah. And we can
Great.
benefit from the good classical subroutines because it's all this combination of quantum and classical at the end.
Yeah, like science is a collaboration rather than we're existing
Exactly.
in a bubble.
Yeah, yeah.
Awesome. Our next question is for the models with provable absence of barren plateaus, these models have proven to be classically simulable. Why is that an issue?
That's it. I also saw this question during the talk. So, I mean, the thing is that if something is classically simulable, what's the point of running it on quantum hardware? That's a bit the whole. The same with Clifford circuits that I was mentioning at some point in the talks. Whenever you have all the Clifford gates, the circuits are classically simulable. This is things that you can compute with your classical computer, and you don't need to run a quantum circuit for that. If we want to obtain any kind of advantage with QML, or with optimization or with VQE, we need to have circuits that have more expressibility than that. And therefore, well, this kind of circuits that I was mentioning that are shallow and have local measurements, there might not be enough.
That makes a lot of sense. And then we touched on this a little before, but what area, field, question do you find most interesting in the quantum field and why? And then if you had an unlimited budget and time, where would you apply yourself or focus?
I see, tricky question. Um, I come from a background of studying many body physics, so this kind of like spin models or models of bosons or fermions that kind of are toy models for materials, let's say. And I think studying phases of matter is very interesting. So both like studying ground state properties of these materials using VQE or SQD or SKQD or other techniques that you're going to see also in the following talks, or studying their time evolution, like the dynamics of these systems, which I believe is one of the first things that we're seeing already now, if you look a bit in the literature, that there's many utility scale experiments that are looking at that, at dynamics of certain models. which is something that is very difficult to do classically. And if you're looking at a model that is composed of spins, it's pretty easily like traduced to the quantum circuit, like using trotterized circuits and this kind of things. So this I believe is very interesting. And I guess I would try to do projects in that direction and continue a bit what I was doing before. Yeah.
Awesome, great question. And then another question that is related is, can you suggest learning paths or resources for quantum machine learning? I know you already talked about the learning platform that we have that has tutorials, but would you like to add on to that?
I think if you search around the learning platform, you'll find interesting resources. There's the variational quantum algorithms course, and there's a lot more that you've seen in the lecture there. And then, well, I don't know. Yeah, maybe I would start with that, and then I would check. Yeah.
Yeah, and then there's also the Qiskit YouTube channel that has a lot of
Yeah.
additional like videos and resources.
Yeah, and then
Awesome,
looking
great.
around in the literature, but I understand that it's difficult also to keep up with with the number of papers that come out, especially with fields like QML or so on. But these things are advancing pretty fast. Yeah, yeah.
Yeah, that makes sense. What would be the advantage of QML versus classic ML?
So this kind of has to be proven. We believe that certain models could show an advantage. In particular, there's the thing I was mentioning before of having quantum data that you want to classify or that you want to process. And for this, it could make sense to use QML, right? Because you kind of might understand better the structures of certain type of data, and you don't need to measure this data, use a classical machine learning algorithm, and then get an answer of this. You can keep everything within the quantum circuit and just get the classification that you need of this data. So quantum machine learning, but usually there's this differentiation made. There's like quantum machine learning for classical data or for quantum data, and then you have classical machine learning for quantum data or for classical data, and there's all these options. That's on one hand. Then I think one of the, I didn't talk about this type of models, but like quantum kernels are also a type of QML model that is very interesting. And here, for example, what we're trying to do is to map the data in a high dimensional space that allows us to separate it in different clusters. And in this case, is having a huge Hilbert space as we have in quantum can be an advantage because this allows for different types of separation that with a classical algorithm maybe you wouldn't get. And depends on the structure you have on your data, it might be better to use classical or quantum. There's also some papers that I saw recently on like trying to figure out that whether for certain structures of data, whether it makes sense to apply a quantum machine learning algorithm or you should already go for classical. And these are all open questions kind of, and people are researching on this.
Awesome. And then we had a previous question from Prince, which said how to parallelize Qiskit codes for complex calculations. He's clarified that he's asking how do we speed up Qiskit code for complex calculations if it becomes slow, unresponsive, or inefficient, which is a really good question in terms of how to troubleshoot, how to make your code better. But I know it's not like a one answer solves all either.
Yeah, I think it depends exactly where you want, what part of your code you want to do this. There's different things in your code that could take a lot of time. Like usually defining the circuits and defining the observable shouldn't take a very long time. But when you transpile them for the hardware, this is something that can take a long time because it's at the end some optimization problem or finding out the best mapping of your circuit into a particular device. And for these, while Qiskit has built-in different optimization levels, you can choose the best one in order to get the best circuit, or you can choose a lower optimization level so that it's faster. But then you're not sure whether you get the best possible mapping. And then once you've done this, you execute your circuit, then applying different error mitigation techniques puts more quantum overhead. So it's going to take longer on the QPU. ZNE, for example, is one of the techniques that has more overhead with gate folding and with PA even more. Other techniques like Pauli ruling don't show so much overhead. So depending on like error mitigation always adds overhead, but at the same time, it gives you more accuracy. And then post-processing the data, once you have it, depends on what you want to do. But in general, yeah, in terms of parallelizing as we would understand parallelizing, then I think we would go more into talking about SQD and this kind of HPC plus quantum and how some routines could be done in an HPC, and then you parallelize what you're doing. For a simple Qiskit code on all the steps of these Qiskit patterns that I was talking about, usually you run these things like one after the other. Yeah.
Awesome. Now, the next question is, do you have any ideas about the intersection of quantum physics and metaphysics?
Metaphysics. I'm not sure what you mean by this. Um,
Yeah, I think
Specifically in
maybe
this
they're referring
context.
to like, yeah, like philosophy or like questions about like why are we here? And Cameron, feel free to clarify. Um, but yeah, sort of, I would define metaphysics as dealing with concepts of identity, time, space, stuff like that. So I think they're
I
asking
see.
philosophy plus quantum physics. I know
I
you're
see. I
more on
see.
the algorithm side,
I
so feel
mean,
free to.
I think this could be it's definitely a very interesting type of discussion, but it could be very long, and I don't really know how to map it to what we've been talking today. I mean, there's the first thing that comes to my mind is all the interpretations of quantum physics, no? And then you have a bunch of different interpretations that we could discuss and which one makes more sense. But yeah, I think this can be a very long thing. Starting this now, we would need another presentation and also no expert on it. It's just more for fun. But I agree, it's an interesting discussion.
Agreed, yeah. And I think there's a lot of cool resources out there that do touch on this. So very interesting question. Now, do you have example of quantum chromodynamics Gauge theories are encoded utilizing a qubit-based representation for Gauge variables?
Yes. Yes, we were actually next week we have a paper coming out on one of these kind of theories, in which we've been implementing many of the things that are discussed in the practical quantum techniques and so on, if you're interested. And there's different ways in which you can implement lattice gauge theories. Like you basically need to make sure that your degrees of freedom are expressed as a two-level system. And then for some of them, it's easier. Like in those cases, we're working with a Z2 lattice gauge theory. And then you have spins on the matter side, and on the links you just express this also as a two-level system. Then there's people that are using Schwinger model. There's ways of absorbing the gauge degrees of freedom into the matter, so that yeah, then you have an easier mapping and so on. Yeah, this could also be a long discussion, but simulating the dynamics or using VQE to get ground states of this kind of lattice gauge theories, it's a very active field of research. There's been very interesting results this year, several publications, and there's many things being done in that regard. Mm.
Great. And then our next question is, how's the accuracy of VQE results affected by the choice of the ansatz?
Definitely very effective. So I mean, at the end, the answer, depending on the answer, they will have shallow or deep circuits, and this is affecting the noise and also the things that I was mentioning in the presentation. No? So you want to have an answer that has enough expressibility so that the ground state that you're looking for can be expressed by the ansatz. Otherwise, you're doing a whole search, but you cannot find a ground state. This means you need to have enough gates for that to be expressive. On the other hand, this means you need to have enough gates, and also that this usually this answer is nice if it's physically inspired, because then you know that you're expressing some area of Hilbert space that has to do with your problem. And this is what we saw with a unitary coupled cluster for quantum chemistry, or the QAOA for some optimization problems, are answers that are built with this physical idea behind them. But then you want something that it's hardware efficient because you have too many gates. First of all, there's noise, but then you also have trainability issues, having too many parameters. You have barren plateaus and so on. So it's one of the most difficult decisions. Like the ansatz, when you're implementing VQE, there's two clear, like two main problems that you have to solve. Is like thinking about the initial state, the initialization, which will also affect having or not having barren plateaus, and the ansatz, and then several things that you can implement that I was also mentioning.
Great. Have you ever considered using machine learning techniques for circuit optimization?
Yeah, I think so. Qiskit actually has the AI transpiler that allows you to, I guess, circuit optimization. You mean like mapping into like the hardware, one of the Qiskit patterns that I was mentioning. And the AI transpiler is doing that, and there's already efforts into using this kind of algorithms for that. It makes sense. It makes a lot of sense.
Some great minds think alike. Our next question is, will we be covering quantum deep reinforcement learning or quantum transfer learning? I don't remember off the top of my head, but I don't think so. If not, can you quickly touch on the world's progress in these two VQML techniques? So I know this is a little out of scope for what we've covered in the lecture, but would you like to touch on this?
Yeah, I don't think it's going to be covered. To be honest, I'm not an expert specifically in these two techniques. So, yeah, I wouldn't be able to give you a good answer right now. As I said, there's many QML techniques. Some of them I'm more familiar with, but at some point I also get lost with all of them. So yeah, sorry for that.
Yeah, I will point this person to the learning platform and the Qiskit YouTube, which has more materials on it.
Yeah, maybe there's something. Hmm.
Awesome. How does the QAOA perform on the max cut problem compared to classical heuristics?
Yep. So I think there was also some question around during the this talk that was asking whether there was some advantage coming from QML or optimization algorithms. And connecting to this, we haven't observed a quantum advantage. Also, there's I mean, in general, quantum advantage has to be well defined. There's a recent paper by some of the people at IBM and some other collaborators commenting on what it means, quantum advantage. What do we need to say that we've achieved it? And specifically for QML, we haven't achieved it either. So when you compare to classical techniques, it's not like we can do better than classical techniques. And also it's difficult to scale right now. As I said, also the classical techniques for optimization are very advanced. But in particular, QAOA for this kind of problem seems to work pretty well, scales well, and it's something that it's promising. And as we go to better and better devices with less noise, and we can scale the number of qubits, these things will become better and better too.
Awesome. What are your thoughts on hybrid quantum classical algorithms beyond VQE and QAOA?
I think it's a very interesting and active area of research. And there's definitely going to be beyond VQE and QAOA, like some examples are these SQD and the SKQD and so on. And I think in the following years, we're going to see more ways of kind of connecting the QPU and some HPC resources and doing algorithms that have some weight both in the classical and the quantum learn. At the end, we want to do something in the quantum computer that it's best done in the quantum computer, but then the rest of the things we might want to do them in a classical computer, which is also very good for some tasks. You know? So yeah, mainly some examples that we've seen right now are these SQD or SKQD, and I think these are very, very promising. And as I said before, I think we're gonna see as it VQE that it kind of started, and then people were looking for all kinds of different variations of the algorithm with the new type of approaches, we're also going to see how these fields grow, and many people are thinking of better ways of implementing them. Yep.
Oh, great. What's your opinion about the idea that quantum information in ML will be more about the data sampling rather than the models?
This could be, in fact, so quantum computers are very good at sampling. Computing expectation values is very costly, as we've seen for quantum chemistry Hamiltonians. We need a lot of shots to get these expectation values with high precision. Maybe we didn't talk so much about the precision there, but this is also very important when you need to solve a model with very high accuracy. And instead, for sampling, we are able to sample pretty fast and to sample from a quantum probability distribution that it's something that in principle cannot be reproduced by a classical computer if it's not classically simulable. So it's believed that some of these sampling algorithms could be the key for this kind of quantum advantage. I recommend you to look at this paper. It's called A Framework for Quantum Advantage, what I was mentioning before, that kind of comments on what would it mean to have quantum advantage, what do we need to say that we've achieved it, and we need to have examples in which we can talk like we have results that can be validated somehow, but that can you can also show that it's better than its classical counterparts and so on. And they discuss the role of variational quantum algorithms there and also the role of sampling algorithms.
Great. And now I think we have time for one last question, which is, what is your favorite algorithm?
Oh, wow. I don't know, favorite algorithm. I mean, the fault-tolerant algorithms are very nice, but very far from being applied right now. So I would say maybe quantum phase estimation. I think they're more elegant in the way that what you get out of the quantum circuit is really like the solution instead of like sampling expectation values. And but they're less flexible. So I don't know if I can choose for one. Right now, I'm working a lot with Trotter circuit, which is not really an algorithm, but it's like doing simulation of quantum circuits and quantum systems, like evolution. And I think that's very interesting. And well, maybe SQD is also pretty nice. So you're going to see more about it. And in this way, it's a good way to end since this is going to be the next sessions.
Yeah, I love it. Well, thank you so much all for your questions, and thank you, Joanna, for joining us and
It was
answering
very
so
nice.
eloquently. And with that, I think this is the end of the Q&A. Thank you guys.